Okay, guys, I want to just spend a little time with you talking about free fall and acceleration due to gravity. I know you should have already taken the PowerPoint notes and you should have watched the video that I put up there, but I think we need to talk about it just a little bit. So, this is acceleration due to gravity. So, when we talk about free fall, like you saw in the little video, we need to think about inertia. And what inertia is the resistance to change in position. And basically, what that means is if something's moving, it wants to continue to move. If it's stopped, it wants to stay stopped. So it's a resistance to a change in position. When we think about inertia, we also have to think about a mass. And when we think about mass, we need to think about how much mass, because I can say that if I have more mass, then I have more inertia. So it's a directly proportional relationship. I also have to think about weight in here as well. And I can say more mass, more inertia, more weight. So all of these things we consider a directly proportional relationship. So I know about mass, I know about inertia, I know when something's falling with acceleration due to gravity, I call it free fall. When something's, or when I have an object, let's say, that's in free fall, then it's, we'll say, is being acted on by acceleration due to gravity, which we call G. So all along when we've been talking about things in the horizontal plane, we've been talking about A. Now that we're in the vertical plane, we're going to talk about G. So any formula that you already have that has an A in it, that A can be replaced with G. Any formula you have that already has an X in it, representing the horizontal plane of motion, that can be replaced by Y, now representing the vertical plane of motion. So all of your old formulas still work. We just have to replace our X with Y and our A with G. So all of our formulas really can be used on these types of problems as well. When we talk about acceleration due to gravity, we should know that G is equal to negative 9.81 meters per second squared. Now, why do we call that negative? We call it negative because that force is directed in the downward direction. And we know at this point that any vector in the downward direction is considered to be a negative vector. We can also say that gravity is equal to the ratio of inertia to force making the object fall. And I can say that it is the same for all objects. So acceleration due to gravity on Earth is the same for all objects. So now when I'm thinking about something falling or being thrown, I have to think about the path of the object, which is one of the things that we talked about in class, yesterday, I guess. So let's talk about that a little bit. We'll call this free fall. Free fall and the path of an object. Make sure that looks like fall. Okay, so we know when something's in free fall, it's in motion. It might start from rest. It might start by being thrown. And we have to pay attention to that when we work these problems. But when I look at the path of the object, I have to think about how is it falling. I can really think about dropped or throw. I can think about something falling off a window ledge. We had a problem earlier about something that dropped off of a building. Those things are being dropped. So they're starting with an initial velocity of 0. When something is thrown or kicked or what have you, let's say that I throw the football, it leaves my hand with some initial velocity. So in those cases, VI has some number attached to it, not 0. In terms of final velocity, you have to pay careful attention to these problems, whether it says the object comes to rest. And if it doesn't say that, then we know that we have to find the final velocity as we start the problem. So if something is being thrown, then it's going to follow the path of a trajectory. It's going to start, move through the air, and return. When it leaves the person's hand, or when it's kicked off the foot or tennis racket, whatever the case might be, I have some initial velocity that is a number in meters per second squared. As this object moves up the trajectory to center, it's being acted on by gravity, just as it is as it returns to its original position. On the way up, gravity is working against it. On the way down, gravity is working with it to get it back to the ground. So in both cases, gravity is the same. Now, if I think about this velocity, and this is true with anything that's moving through the air, that's following a path, and we're going to call this path a trajectory. Oh my goodness. So this whole path is called a trajectory. When this object gets to the top of its trajectory, it has been acted upon by gravity enough that it almost stops for a split second. And if we look at a slow motion camera, which we will eventually, I'll show you some pictures of that, we will see that my velocity becomes 0 meters per second for just a tiny bit of time. Then it begins to fall again, and it's falling due to acceleration due to gravity. When it gets to the bottom of the path, it has some final velocity. My final velocity is equal to some number of meters per second squared. As it is taking the path upward and then this path downward, we assume that we have no air resistance involved, so that I can say that these two things are equal when I'm following the whole path. You have to pay careful attention to the words. Is it asking you for the total distance covered? Is it asking you for the distance to the top of its path? Is it asking you for the distance from the top of the trajectory where velocity equals 0 to when it strikes the ground? So you have to really pay attention to these to figure out how much of the time you're going to use. It takes me some time to move up, and it takes me some time to move down. If I have no air resistance, then I know that my time up is equal to my time down. So if it took me 1.5 seconds to reach the top of my trajectory, it's going to take me 1.5 seconds to reach the bottom of my trajectory. If I want to know the time for the entire trip, then I use all of it. If I want to know time to peak, then I would use half of it. Okay. The other thing that I have to think about when I'm thinking about how this trajectory is moving, or how this object, I'm sorry, is moving, is perhaps I have an individual, we'll say, that's standing on the top of a building. Okay, there they are. This will be situation A. This will be situation B. In situation A, this individual is holding a ball, and they just drop the ball straight down. This distance would be your delta y. Of course, it's being affected by g, and it's going to take some time to strike the ground. Over here, let's say I have an individual that actually throws the ball up. That ball is going to travel to the top of its trajectory, and then it's going to begin its way down. Up here at the top of the trajectory, I know my velocity equals 0 meters per second. So it starts at some velocity, it travels to 0, it returns to final velocity. When this object that's being thrown reaches the same point across the grid, this position VI is equal to VF. Those are things that you have to think about just a little bit as you're working these problems. Okay. 2 new formulas that I want you to put on your card. The first one, this formula will work when an object starts from rest, and let's say you're looking for distance. We can use this formula. You should remember that we had a formula on your card, delta y equals VI delta t plus 1/2, it would be g, in this case, t squared. If I have something that starts from rest, that means this whole thing is 0. So I can get rid of it. And in these problems, I can say delta y equals 1/2 g delta t squared. It's a way to find my distance. Only if I have an initial velocity of 0 does this work. If I have a velocity other than 0, I can't use the formula. So that's a new formula you can put on your card. And then the second one is when the velocity of an object is in free fall, let's say velocity when an object is in free fall. That means it's moving. We don't have a VI, we don't have a VF, we're just talking about velocity at this time. In that case, we can use a formula where velocity is just equaled to V equals GT. So gravity times time tells me what velocity is. I just need to know like the number of seconds the object's in the air to be able to work a problem like that. Okay, go ahead and put that one on your card as well. And then I want to talk to you a little bit about your lab. On your lab at this point, I'll work a problem or two with you. On your lab at this point, you should have all of your distances. So you should have your distances. And you were already supposed to have those averaged. Now what I want you to do is to take each distance, and that should be in meters, and I want you to use delta y equals 1/2 g delta t squared to calculate your calculate your time for each fall. So yes, I believe most of you had the 15 falls. So I want you to calculate for those. So you'll end up with 15 times. And I want you to average those. And then I want you to calculate the velocity of the meter stick using average distance, which is your delta y, and your average time, which would be your delta t, using delta y, using v equals gt. So you should do that. So then you should have your average distance, you should have your average time, and you should have a velocity. And you can just put that information on the back of that sheet. Since you guys weren't here to get the second sheet and you really don't need it, but you can put it on that. Then the other thing that I was going to show you today were just a couple of the example problems. Let me find the sheet that has the problem on it. Okay, so we have a problem, and this is posted on Classroom. And I couldn't remember if you guys got it before you left or not, so I went ahead and put it on Classroom. But the first problem says a student hits a volleyball so that it moves with an initial velocity of 6 meters per second after being spiked straight downward. The volleyball starts from 2 meters above the floor. How long will it be in the air before it strikes the floor? Assume no other players touch the ball before it hits the floor. So it never says that this ball comes to rest. So let's look and see, what do I know? In this situation, it moves with an initial velocity of 6 meters per second after being spiked downward. So I know that my VI equals negative 6.0 meters per second. I also know that it traveled. My delta Y is equal to negative 2.0 meters per second because it was moving downward. I know G because that always equals negative 9.81 meters per second squared. I do not know a time, even though that's what I'm asked for. And because it doesn't say the object stops, I know I need to have a VF also. So when I look at my formulas, I don't find a formula that I can use that's going to work to give me time right away. So I have to hop in and I have to use this VF squared equals VI, excuse me, VI squared plus 2G delta Y. And then I'm just going to plug in what I know. I don't know VF. And it will be equal to negative 6 meters per second plus 2 times negative 9.81 meters per second squared times negative 2.0 meters per second. Okay, so that should be saying VF squared. I'm not sure what I did there. And then when I plug that into my calculator, I do all the math. Let's see, what do I get? I have negative. Oh. Go ahead and work it out. So then it looks like I come up with VF squared equals 34, oh, no, wait a minute.